Hi everyone, and welcome to the Unit 7 review session. This unit focuses on bonding and intermolecular forces. And let's get started with a little bit of review of terms. All right, our first one is electronegativity. Remember, electronegativity is when two atoms are sharing a pair of electrons. Which one of those atoms is going to pull the electrons closer to itself that value is called electronegativity. So what we find, the general trend, all right, is that our nonmetals, all right, those to the right of the stair step on the periodic table have high electronegativities. They really want to gain electrons. They want to pull electrons towards themselves, whereas our metals tend to have lower electronegativities. All right, couple things to keep in mind. Your group 17 is going to have your highest, all right? So on the periodic table, the trend is it increases from left to right and then increases from bottom to top. So that group 17 has very high, and then up here on the right. Remember, noble gases we don't talk about in terms of electronegativity because they don't want electrons at all. They are happy with their arrangement. All right, electronegativity is going to come up quite a bit when we talk about polarity, so just hold on for that. Now, when you see the term intra, that means within. So intramolecular forces are the forces within a molecule. We call these bonds, and you should be familiar with three types. We have ionic bonds, covalent bonds, and then finally metallic bonds. All right, we spent a lot of time talking about properties of ionic. You should know general properties of metals and general properties of covalent, all right? Remember, ionic bonds dealing with ions, so when electrons are gained or lost. Covalent is the sharing of electrons. And then metallic, we didn't spend a whole lot of time talking about metallic bonds, but it's where electrons jump from one metal atom to the next. That's why metals are such good conductors of electricity. All right, next up was Lewis dot structures, and we spent a lot of time this unit doing Lewis dot structures. This is a model that we use specifically for covalent compounds, all right, to help us understand what's going on in that compound as far as the bonding goes. Couple reminders when it comes to Lewis dot structures, all right? Let's go ahead and I'll give you an example. Let's say I give you the compound CCl4, and I ask you to do the Lewis dot structure for that. First thing you're going to do is count up the valence. That's based on the location on the periodic table. All right, group 1 has 1 valence, group 2 has 2 valence. Group 13, 3, 14, 4, 15, 5, 16, 6, 17, 7. You get the idea. All right, so you're going to count up those valence electrons for the whole compound. So carbon's part of group 14, so it has 4. Chloride is part of group 17, so it's 7. 7 each, but there are 4 of them. So that gives you 28. All right, next you're going to choose your central atom. Central atom is the first one written or the only single. So you're going to have chlorine there. You're going to then, imagine there's 4 sides around it. And I'm sorry, you have carbon in the middle, then chlorine around the 4 sides. You're going to then connect them with lines. All right, those lines are bonds. Remember, a bond is 2 electrons. So now you're going to make sure everything has an octet. All right, remember all atoms want 8 electrons around them, with the exception of hydrogen only wants 2. Okay, so here we go. I need to now check, did I use the proper number of electrons? Well, if I had 4 coming from carbon and 28 coming from chlorine, I should have a total of 32 electrons. All right, so I have 8 and 8. All right, which is 16, then another 8, which is 24, and then that's 32, and that works out well. If you find that it does not work, that means most likely you need to use a double bond or a triple bond. You should review, all right, my notes video for Lewis dot structures if you're not feeling very comfortable with those. One of the main reasons why we do Lewis dot structures is to help us determine the shape of the molecule. And when we are talking about shapes, we are talking about something that is called Vesper Theory, valence shell electron pair repulsion. All right, and that's just a very fancy way of saying that electron pairs want to get as far away from each other as they possibly can. All right, and this is going to lead us to our 5 different shapes. And these shapes are all based on what's going on with that central atom. If you find around the central atom that you have 4 what we call shared pairs, and again, this is around the central atom. All right, if you have 4 shared pairs and 0 unshared, that is always going to be what we call a tetrahedral. Okay, shape. If you have 3 shared pairs and 1 unshared pair, that is a trigonal pyramidal. That's a pyramid. If you have 2 shared pairs and 2 unshared pairs, that is going to be bent. All right. And if you have 3 shared pairs and 0 unshared pairs, that is trigonal planar. And finally, 2 shared pairs and 0 unshared, sorry, I'm getting a little off kilter there, that is going to be linear. All right. So please remember a couple things. It's always around the central atom. If that central atom has a double or triple bond, for this scheme, we consider that double bond just to be 1 shared pair. All right. Please make sure you understand the general shapes of these. All right. That we did, again, you can go over in the video and see that. Okay. Now, next thing we talked about is you can use these shapes to help you figure out whether or not a molecule is polar or non-polar. All right, and you're going to do that. In order to be polar, you have to first have polar bonds. The next thing is you have to have a shape that allows for there to be a side that's positive and a side that's negative. So first off, a polar bond is really any bond between 2 different elements because they have different electronegativities. One of them is going to pull the electrons a little bit closer than the other. All right, but as far as shapes, if you're a tetrahedral, all right, so if you're a tetrahedral, tetrahedrals can be polar or non-polar. They're going to be polar, or actually, let's start out, they're going to be non-polar if everything around that central atom is the same. So for the example, methane here, that is a non-polar tetrahedral. But if all of the sudden, instead of a hydrogen there, I have a chlorine, this one is going to be polar. So tetrahedral, if all 4 are the same, then you have non-polar. If any one is different, you're going to have polar. The same goes for trigonal planar and for linear. All right, if they're all the same around the trigonal planar, it's going to be non-polar. If any one of them is different, it's polar. Linear, same situation. Our last 2 shapes, bent, which remember is like water. It's actually that shape. All right. Bent is always polar. And so is trigonal pyramidal. All right. Always, always polar for those 2. Okay. So that's kind of where the general is for those shapes. Okay. Now that we've talked about the bonds, what we want to talk about are the forces that hold one molecule to another molecule. And these are called intermolecular forces, also known as van der Waals forces. All right. Dipole is between 2 polar molecules. And it is that attraction between the partially charged sides. So water is our classic example. All right, where oxygen is partially negative, your hydrogens are partially positive. If 2 water molecules get near each other, all right, that partial positive and partial negative end are going to be attracted to each other. That is an example of a dipole-dipole force. All right, dipole just means polar, so polar to polar. all right? And that is that force. Please remember that hydrogen bonding, worst name in chemistry, but nothing we can do about that, is specific, is a specific type of dipole-dipole force, all right, where you have the strongest type of dipole-dipole force. So make sure that you're comfortable with hydrogen bonding. London dispersion forces are just the random movement of electrons, and they occur in all elements, or I'm sorry, all compounds, but they are the only force for nonpolar molecules. All right. This is a very weak intermolecular force, and this is why nonpolar molecules, if they are going to be liquids, they will have a very high rate of evaporation. Okay. All right, so just a couple last things to remind you of. All right, what state of matter would you predict a substance would have if it has low molecular mass and was nonpolar? Well, we just talked about nonpolar means it only has those London dispersion forces. If it's very light, all right, then really it can work against gravity pretty easily. So if you are low molecular mass and nonpolar, chances are you're going to be a gas. All right, and that is because you don't have a really strong reason to stay near the other molecules around you. All right. Hydrogen bonding, as I mentioned before, please make sure that you are comfortable with that hydrogen bonding when it occurs. All right, so you've got your hydrogen bonding, occurring when hydrogen within the compound is bonded to oxygen, nitrogen, or fluorine, okay? And it is, again, the strongest type of dipole-dipole, and it is happening with water, so really important. Final thing that we did in this unit was talk about the properties of water. All right, important things to make sure you are comfortable with is the term adhesion and cohesion. All right, cohesion is when water is attracted to itself. All right. And adhesion is water's attraction to others. Okay, and this causes all those good properties, that cohesion of water, like surface tension, all right, all of that good stuff. So please make sure that you review those properties of water. All right, everybody, good luck on your test. Take care.